So this is the bifurcation diagram of the lac operon, and it represents a saddle node bifurcation. Now, this bifurcation diagram is so important. I want to take you through the construction of the bifurcation diagram because it's something that we're going to be doing a number of times. So we're going to let the R parameter vary. Remember the R parameter, it's the rate of degradation. It's the thing that produces the bifurcation. But we're going to let that vary. And we're going to start with R at a very low value, 0.16. Now, up here, we're showing you the state space, the X state space. And for this value of R, there is a single equilibrium point at the very high value of X. So this is the state space that is going to ensue for that value of R. So now what we're going to do is take that state space, turn it vertical, and stack it up right over the point R equals 0.16. And that represents the state space for R equals 0.16. Now here's 0.17. 0.17, the equilibrium point is moved in a little bit because as R increases, it intersects that sigmoid at a lower value. So for R equals 0.18, again, we have a single equilibrium point, but it's at a slightly lower value of X. 0.19 now, you see what happens at 0.19 is we suddenly have the appearance of a new red and blue pair of equilibrium points. And this is the saddle node bifurcation. We now have two new equilibria. But we're going to take that and we're going to stack it up right above R equals 0.18. Now, if we look at R equals 0.2, we see that the two equilibrium points are now a little bit separated. There's a tiny little bit of daylight between them. We're going to take that, and again, we're going to turn it up, and we're going to stack it at the right point. R equals 0.21, same thing, stack it up. R equals 0.22, stack it up. Now you're beginning to see what's happening. The high equilibrium point is coming down, and the pair, the new pair of an unstable and a stable are starting to separate from each other as the unstable is heading up and the stable is heading down. So where is this going to end? Well, here's another value of R, higher value of R, 0.26, 0.27, 0.28. Still, the two lower equilibrium points are separating from each other, and the high equilibrium point is coming down. 0.33, 0.34, 0.35. So pretty soon, as you see, the red unstable equilibrium point is going up, and the blue high stable equilibrium point is coming down, and they are eventually going to collide with each other and annihilate each other in a reverse saddle node bifurcation. So that's still 0.5. And again, still they're separating. And now 0.54, 0.55. Now, at 0.59, the two upper equilibrium points, the unstable in the middle and the stable at the top, have coincided with each other, they've collided with each other, and they have annihilated each other. And we now have left only the single stable equilibrium point at the low point. And that is, of course, a reverse saddle node bifurcation. Now we're just going to take away the lines. And by melting away the sticks and leaving only the equilibrium points, we show how we construct the saddle node bifurcation for the Lac operon.